Yeah, the session is now recording. So, welcome one and all to our eighth weekly discussion session for the Physics of Nanoscale Devices NPTEL course. As always, my name is Jyoteshwaran. I'm a PhD student from the ECE department of IIT Roorkee. So, as I had mentioned last week, in the end of last week's session, uh, we shall be starting with this topic that we kind of left from last week. So we'll look at realistic 2D channels and the idea of 2D subbands. We had already seen this for the 1D case. Please refer to the previous week's slides for that. So we'll essentially repeat that exercise for the 2D subbands very quickly, and then we shall move on to the idea of MOSFETs. So this is going to be a bit of a detour because right now what we shall be discussing are long channel MOSFETs. We shall be looking at conventional classical bulk MOSFETs, and it's just kind of a refresher to see what the properties are, what are the ideal characteristics that are expected, what are the sources of non-ideality, how do they manifest themselves in the device, and how does that alter the characteristics. So that is what we shall be looking at today, and that is primarily what the content of this week's lectures and assignment is. So we'll solve one or two examples, which again ought to help you solve the assignment problems. So yeah, let us begin. So this is again last week's stuff. So if we look at a realistic 2D ballistic channel, now how, so this realistic 2D channel, as I mentioned last week, is also sometimes referred to as a quasi 2D channel. So the quasi here refers to the realistic aspect because in reality, even a single atom is a three-dimensional object. Like the electron distribution, the wave functions, they have a 3D distribution. So there is, like, we are treating atoms as 0D objects only in the sense of electron transport. In that, I cannot arbitrarily move the electrons along any of the axes. They are bound in a certain region. So that confinement is essentially what we were referring to as a zero-dimensional system. Similarly, as we are moving further and further and further, we have quasi 1D and 2D systems where the idea is essentially what is presented here. Now, I have a material where the electron is free to move in two directions, like relatively unconstrained to move in two directions. In this case, the x and y directions, and it is constrained to move in the z direction. There is a very high degree of confinement in the z direction. So this region right here, this is the confinement. Now, wherever there is confinement, as we have been seeing since week 1, this implies automatically energy is quantized. And one more thing that we should remember is energy is quantized, yes. And like this is one of the, like this was the second or third problem that was solved in this course. So the idea is if it is confined in one direction, then E min, the minimum possible energy, is no longer zero. It becomes non-zero because there is always going to be a delta non-zero delta P, and since there is a non-zero delta P, there is going to be a non-zero kinetic energy to this particle which is confined in such a manner. Okay, so now how do I write the, so the things that are needed are the dispersion relation and the expression for the density of states and a sketch for the first four subbands. So these are the three things that we need to do. The dispersion relation is the EK relation. So let us see how that goes. First and foremost, we know that the electron is free to move in the x and the y direction. So the energy is going to be the standard expression that we have been using thus far, 2m star plus h bar squared ky squared upon 2m star plus, so this is kx and ky, and now what about kz? Now this is confined, therefore E min can no longer be 0. So in this direction alone, I will have to treat this as an infinite well of sorts. So the energy for that is going to be h squared pi squared. So the height along which is confined is h. Okay, h is a very poor choice of letters because it also matches with the Planck constant. So you know what? I'm going to write this as, uh, let us say, let us call this d, the depth. Okay, so yeah, n square pi squared, h bar squared divided by 2m star d squared, and this n is corresponding to the z direction, so I shall call this nz also. Okay, so 2m star d squared. Now over here, the conditions are kx, comma ky are both, just one moment. Uh, sorry, sorry. Yeah, there seems to have been a sharing issue here. Let me just. Oh, really sorry for that. Yeah. But not to worry, like the whole sequence has been recording. So people who are watching the recorded version of this would not have noticed any issues. And you could have also just spoken up over the voice channel to tell me that I was not sharing things correctly. Yeah, just one moment here. Let me move back. Yes. Yeah. All right. So here kx comma ky, they belong to R plus. These are positive real quantities, and they can also be negative, but there is no distinction between a negative k value and a positive k value, because that just, like, it has the same kinetic energy. So I'll just take the positive values just to make this clearer. Yes, R plus, and nz is equal to 1, 2, 3, and so on and so forth. And this set is, can alternatively be written as, or nz belongs to z plus positive integers only. It cannot take zero value because again E min cannot be zero. Now, how will this? Okay, so this is the dispersion relation because there is an E and it's related to K and the NZ. So I can also additionally write E is equal to some function of Kx, comma Ky, comma NZ. So this is my dispersion relation. So part one of this problem is done. Okay, and quickly a new slide. Okay, and yeah. So the second thing that we have to find out is the expression for the density of states, and then sketch the density of states for the first four subbands. So now DOS for a 2D system. Of a 2D system, we know this to be m star divided by pi h bar squared. It has no energy dependence. So this is what has been derived from our, you know, one second, sorry. Yeah, apologies for the interruption. Where was I? Yes. So, yeah. So this is the density of states. However, now what we need to remember is I'm not going to go too far into the explanation here because I'm going to refer to the previous week's slides because I had a rather in-depth discussion on that matter about why the density of states is not exactly this. Now I will just point out that E min, the minimum energy for this quasi 2D channel is going to be this pi squared h bar squared by 2m star d squared. The energy is not going to be any lower than this because kx and ky can be 0, but even then nz cannot be less than 0. So this is the lowest possible energy, which implies below this energy level. So let me call this energy E0. So below E0, there cannot be any density of states. So first and foremost, I need to replace this by h of E minus E0. So what is h? I will just recall these things. So this is from Professor Vishwen's notation. So this is the Heaviside step function. I use a more conventional like electrical engineers notation where we have the big theta notation for this function. So it's called theta also, like they are both equivalent. And so I'll just continue using theta because it's, very old habit for me. So theta of x equals 1 if x is greater than 0 and 2 if x is less than 0. So the theta function has like several applications. Most commonly, the Fermi-Dirac function at t equal to 0 Kelvin is a sum of theta functions. And the integral of a Dirac delta function is a theta function. So there are many, many properties. Oh, not 2. My God, I was about to write 0 and then I just stopped. 0 for x is negative. Yeah. All right. So in this case, when E goes below E0, this quantity will automatically become 0 because the argument for this function will become 0, sorry, negative, and therefore this function will become 0. Note, however, that this whatever value of kx and ky that I have, for n equal to 1, I will have a certain values of energy. Then for the same kx and ky, taking n equal to 2 will give me another set of energies. So essentially, nz going to nz plus 1 implies more energy states. So when nz goes to nz plus 1, I know E. Okay, let me just introduce a new notation here. Remember that energy is a scalar quantity. It does not have any direction, just a magnitude. But just for the sake of convenience, let me call this EXY. Okay, so when, let me get rid of this for a second. So now my total energy for in this quasi 2D channel is going to be Ex comma y plus E0. So this is the case where nz equal to 1, and then we may have Exy plus 4 E0. Oops. This is the case where nz equal to 2, Just 1 second, we seem to have a new attendee. Yeah, welcome to the discussion session. So, uh, oh God, yeah, yes, we're back. So as I was saying, yes. And the third case, since I've asked for the four subbands, let me write all of them here. EXY plus 9 E naught. This is the case for NZ equal to 3. And EX comma Y plus 16 E naught. This is the case for NZ equal to 4. Notice that even while fixing the Kx and Ky values, I can still have as many, infinitely many distinct energy levels by varying Nz. So now how is this going to look like? As long as Nz is not 2, only these energy levels will exist. So, uh, and for each of this, even if I set Kx and Ky equal to 0, the lowest possible energy in that subband is going to be this quantity right here. Either 4 E naught or 9 E naught or 16 E naught. Okay, so now what does that do to our density of states? Yeah, so for those of us who are newly joining these sessions or watching these after a break, I've finally figured out how to draw a straight line on PowerPoint. So, yes, that. All right, so now let me choose a scale of appropriate length. So let me say this is E naught, therefore it's going to be 4 E naught, and you know what, that's too big. I'm going to choose it at the quarter point over here. So, therefore 4 E naught is going to be right here. This is going to be 8 E naught. Therefore 9 E naught is going to be here. So this is E naught, 4 E naught, 8 E naught, 9 E naught. Therefore this is going to be 12 E naught, and this is going to be 16 E naught. I'm essentially taking it as 1/4 of this line segment here. Okay, so yeah. So there is a theta function here, essentially a heaviside step function here. So the density of states is going to be, let me try to use some colors. I should actually go it up from here. Yes. So it's going to go like this all the way. And then the second curve, let me use a slightly different color here. It's going to rise from here. And again, this is going to join over here. And then, so this is essentially the point. This is m star upon pi h bar squared. So this is that value. Okay. And then for 9 E naught, different color, which one shall we use? Yeah, why not? think it is. And then and finally at 16 E naught. Oops. Check this correctly. Here we are. So these are just overlapping lines. I'm just slightly displacing them so that they all become visible. Okay. Now the density of states is going to have to be the sum of all these subbands because I want the whole channel's density of states. So how is my actual density of states going to look like? So for that, let me trace over that with black. So it's going to go up all the way up until this point, and then it's going to, this yellow step function is going to add to this, so I'll get another step over here. No arrows. And then it will again move flat up until this point. Not quite there, up until this point here. And then from here, it's again gonna take another step up. Yes. And then it's going to stay flat all the way till here. And after that, it's going to shoot up one final time and continue like this until 25 E naught, where it will take another step. So this is how the density of states is going to look like, and the expression corresponding to this. So for a quasi 2D channel, the density of states is going to be, so D quasi, let me put the quasi above, 2D of E is going to be, of course there is a constant factor outside, so pi h bar squared summation, summation I equal to, or let me say n equal to 1 to infinity h of E minus n squared E naught. So this is the expression. So it is going to be a sum of step functions, and this is how it's going to look. Now, if you make h to be larger and larger and larger, these values of E naught will become smaller and smaller and smaller. And what is essentially going to happen is the density of states will actually, like even now you can see that it follows, the peaks follow a kind of a curve profile. Let me see if I can sketch that reasonably well. Okay, yeah. And then it's going to go up to this point and this point. It's going to go like this. Now, if you look at what this line is, this curve is actually y is equal to square root of x. So the quasi 2D material channel's density of states will actually reflect that of a 3D density of states. Kindly refer to last week's notes where I established that a quasi 1D channel's density of states will actually resemble a 2D density of states. It's essentially a straight line with some fluctuations. Okay, so yeah, this is all parts of that question. So last week's content is now officially done. Yeah, now moving on to our topic for this week. And this is going to be fairly straightforward because many of you might already know all of these things. So I will try not to linger too much on that. So I'll just quickly go through things. So now we are looking at a MOSFET. The structure is given like this. So this is a P-type silicon substrate MOSFET, which is an N MOSFET because again conduction takes place through a channel inversion. So this inversion layer over here, let me see if I can draw like this. Of course I can. So this line and this line right here. So these inversion layers is where the conduction takes place. Of course, we are looking at transistors being MOSFETs being worked in the enhancement mode, not in the depletion mode. So we essentially cause a channel inversion in the substrate, like not in the substrate. We cause a channel inversion which allows for current carriers from the source to move to the drain. The channel inversion is achieved by applying a gate voltage that is greater than a certain threshold voltage. And then we try to draw a current out of the drain. Okay. So uh, MOSFETs are three-terminal devices, and the gate voltage controls the conduction properties of the channel connecting the drain and the source. Again, this is something most of us, if not all of us, should already know. So now let us start from the very basics. So draw the equilibrium band diagrams for the following structures. So for a PN junction, for a PNP bipolar junction, and for an N-channel MOSFET. So how are these things going to look like? So first for a PN junction, so to begin doing that, yes, and let me switch this to green. Yeah. So a P-type material, so this is a P-type material. The band diagram is going to be the conduction band and the valence band. The intrinsic Fermi level is going to be somewhere in the middle, slightly displaced above or below depending on the effective density of states. But the donor level is going to be for a p-type material, it's going to be over here. So this is the quasi Fermi level. So this is the not donor level, this is the acceptor level in this case. So this is the conduction band. So this is the CB, or rather I can just say EC and EB. And similarly for an N-type material, we have now the donor level is going to be up closer to the conduction band. So I have an ED here, and then I have my E conduction and E valence. I'm assuming same silicon or the same intrinsic semiconductor is used and different dopants are considered. Now let us look at the three. Yes. So A is a PN junction. Now for a PN junction, we know that the Fermi levels have to be aligned. In this case, the quasi Fermi levels are aligned. So let me draw that as a reference line. and let me say this is EF for the device, and since the P side is here, then my valence band is going to be up here. Let us say this region I'm leaving for the junction. Since this is the N side, the conduction band is going to be here. Conduction band is going to be all the way up here. Valence band on this side is going to be here. And I will just connect the two. So this is a PN junction. EC and EV. Now, so this is the band diagram for a PN junction. Oops. And this is stuff that, you know, technically speaking, even people who are finishing their high school can do. Now we have what? We have an, oh no, we have an PNP bipolar junction transistor. So once again, uh, the Fermi level has to be aligned all across the device. So we'll take a longer reference line. So this is the EF, and I have P, N, and P. So we are going to have the valence band over here, the conduction band over here, and the valence band over here again. And oops, EC and EV, and this is P N P. So this is a bipolar junction transistor. So this is a PNP BJT. And for our last part, now how does the band diagram of a MOSFET look like? Let us look at what's happening here. I have an N silicon, and so this is for what? This is an N MOSFET. So N MOSFET is going to be N type silicon, and P type silicon in the middle. So we are going to have again EF and we shall have the oops yeah n-type material here, so the conduction band is going to be over here and the valence band is going to be over here. You know what, I'll close this thing up a bit. Okay, and then the conduction band again. The upper conduction band is going to be over. Oh, for some reason that line just vanished and it won't reappear. Yeah. So the band diagram is going to be like this. Now you can ask, why haven't I made the lines as rigidly over here. There is a straightforward reason for that, because we make these rigid demarcations. Essentially, we show this uh, gradient of the conduction band and valence bands only when we have a bipolar junction. Essentially, only when we are concerned about the depletion layer that forms between the junction, and the depletion layer width is what that controls the transfer of carriers. Whereas when we are looking at an NMOSFET, so this is an NMOSFET, of course, operating in the enhancement mode. So, no, not enhancement mode, in the depletion mode. Sorry. Yeah, this is also for the depletion mode. Good thing that I did not write it, because we deplete it and then cause the channel inversion. We don't just enhance the device. Okay, so yeah, in a MOSFET, however, we are not particularly concerned about the depletion layers here, because, as I just mentioned, we invert the channel. So when the device is conducting, when a MOSFET is on, there are no junctions between the source, drain, and the channel. It acts as a single contiguous, um, environment. There is no breaks. Whereas if I have a bipolar junction transistor, then the collector, base, and emitter are distinct regions, and the junctions between them play a very important role in the conductivity properties of the device. That is not the case in the MOSFET, which is why I'm not too keen on drawing these straight lines for a MOSFET. So question one is done. Now, what are the characteristics that I expect from an ideal MOSFET? So the idea here is to not go into any of the device properties or material characteristics yet. The notion is, just one second, please. Just yeah. So as I was saying, yes. So now this is just an ideal device. We are not concerned about the materials. We are just saying I have a three terminal device and what kind of a behavior I want it to have. So right now, this device is a lateral black box. Okay, so again, people who have done electronics or electrical engineering will be familiar with black box models. But technically speaking, even people from other disciplines may have been exposed to those things. However, I'm not familiar how those concepts are introduced to uh, those people. So yeah, this is kind of a limitation of my own. So I have three terminals to such a device. Yes. Okay. Yeah. So I have the gate, I have the source, and I have the drain. Now this is my ideal MOSFET. Like, the point is, I need to understand what kind of a behavior I need here. Then I will go about considering different physical implementations of the same, like you know like physical implementation that will give me similar characteristics and properties. So yeah, I have the gate, source, and the drain. Now, this can operate in two regimes which are defined by a threshold gate voltage. So, essentially, what is the first property that I want? If Vg is less than Vt, then it implies stay in mode 1. I don't know what that mode 1 is. Well, technically we do, but for a second, let us assume that we are not even considering that. Vt implies it goes to mode 2. Now, using our common sense, we can say that if the uh, just pardon me for a second. Yeah, I apologize for the repeated interruptions. The thing is, I have a cold, and I really don't want to sneeze into the mic. So whenever I feel like sneezing, I'm like pausing everything and turning away before I sneeze. I mean, while listening to the session, I can what to say like imagine that it will be extremely annoying if somebody just sneezes willy nilly. So yeah, coming back. Now, when the gate voltage is less than the threshold voltage, like typically I will understand that when the voltage is low, current is going to be low. That's Ohm's law. So there's going to be low current and high current. So when I have a low current and a low voltage, I will say that this is the state that I refer to as the off state. Okay, and this is the state that I shall call the on state. Different names are there. It's called the cutoff mode and the active mode and so on and so forth. Okay, and below the threshold voltage. Essentially, the idea is when I say below the threshold voltage, what I mean is moving above and below the threshold voltage. Below VT. Like if I have a source, a signal source that is having a fluctuating or time varying voltage that is moving above and below Vt in some pattern, then my device will move from the on state to the off state corresponding to the value of the voltage coming from that signal source. So that is what I mean when I decide to take my MOSFET below the threshold voltage, I can use it as a switch. And channels. Oh my god. Okay, my English seems to have broken down here. Behave yeah, as a variable resistance. Yep. Yes. So above the threshold voltage, I want the MOSFET to act as a variable resistance. So the whole idea of a transistor is it has a conductance and a resistance and a variable resistance. So that those two words are essentially combined to give me the idea of a transistor. In case anyone here did not know, a transistor is derived, it's a portmanteau essentially where I combine two different words to form a new word. So I have what is called a transconductance and a resistance. So that's what I shouldn't say, a resistor. And this gives me the idea of a transistor. Essentially, I have a third terminal with which I can control the value of the resistance across two fixed terminals. So, second condition is, so second is the switch rule. So, if, yeah, so switching above and below Vt makes the device switch. And three is at V greater than Vg greater than Vt. the, or rather, let me say VDS, not VDS, RDS is varying with VG. So these are the three characteristics essentially. Whatever I've written in words, I've written them in terms of certain parameters. Now, even before we look at semiconductors, which is what the MOS part confirms, some of you might already realize that I can achieve this with essentially, just a vacuum tube with 3 electrodes. I can have a vacuum tube device like, I mean, I'm good with straight lines, but curved lines are still my greatest enemy. So, yes, I have this kind of a device where I have one electrode here and one electrode here and one electrode here, where this acts as the source, the drain, the gate, and just very low density gas here, so that the electrons that are emitted from this plate are not absorbed anywhere in the middle. I can actually make this behave, show all these properties here, like very in a very straightforward manner. And in fact, these were the first transistors that were constructed. So these are essentially known as vacuum tube transistors, also known by an older name before the idea of transistors was developed. These were also called triodes. And it's not like these devices are out of use now. These the devices are still used in places where we need high power applications, because this device, since it is just a glass tube and essentially some noble gas, argon or something in the middle, that too at a very low pressure, these things can carry kilovolts of like operated kilovolt range, and they can carry very high currents. So whenever we need high power, high voltage, high current applications, we still use vacuum tube transistors. And if anybody is a fan of uh, rock music or things like that, vacuum tube transistors are used to construct amplifiers for that to this very day. Like, even though we can use semiconductor amplifiers for those applications, musicians still prefer vacuum tube transistors for many of its characteristics. So what we need to understand here is that the ideal transistor is actually a device that has been realized in many different forms. The reason why we are looking at the MOSFET is the primary reason. Of course, many here may know CMOS and every other subsequent fabrication technology that has come around. The idea, the reason for looking at MOSFETs are, I can make these devices very small. I can pack a very large number of them onto the single circuit. Like, I can essentially make integrated circuits, and large scale and very large scale integrated circuits. That is the whole point of this course. And now we are kind of trying to push beyond that limit and make these MOSFETs even smaller and smaller and smaller, essentially hitting the ballistic limit. So that is the only reason why MOSFETs are special. It's because I can make them small as apparently quite small. I can bring it down to nanometers. But if I need a vacuum tube transistor, I'm at least going to need a few centimeters. I cannot let these two electrodes touch each other. If they touch each other, they're going to short out, and things are going to catch fire. So they need to be placed at a significant distance for this device to operate safely. In fact, the very first computers were built using vacuum tube transistors. So that is the whole essence that I want to convey here, that transistors of every kind, FETs or even BJTs, like, the idea is to first understand what kind of device characteristic and property that I want. And then, based on whatever we know about the materials, we should try to construct devices which can exhibit those properties. So a very integral part of the knowledge that we need to acquire while we are dealing with subjects like these is to treat the devices as systems. Like, start with something as simple as a PN junction diode. It's a device that allows current flow in one direction and blocks current flow in the opposite direction. That is all I want. Now, again, it's possible to have diodes using vacuum tubes. Vacuum tube diodes are also a thing. Uh, in fact, virtually every semiconductor device we can look at has a vacuum tube implementation. So the idea is to take another physical substrate, a physical material, a physical base upon which we can construct a similar functioning device. So it is important to understand the function of the device and then move on to understanding what happens to the like other non-ideal characteristics depending on the materials that we have chosen. And the ultimate aim is to approach the ideal behavior as close as possible. Okay, moving on to the next slide. So draw the output and transfer characteristics of an ideal MOSFET. So remember this diagram here. So the output is always going to be IDS. Okay. Now remember, if IDS is the output, then what is going to be the input? Shouldn't be very hard to imagine. It is going to be VDS. And what ultimately controls the ratio between IDS and VDS? That is this notion of transconductance, and that is controlled by the gate. So when I'm talking about the transfer characteristics, I'm referring to the VG. I'll write what VGS is in a second. So let me quickly go back here. So usually when I'm applying voltages here, what I do is, let me draw this mock-up of this diagram here for a second. Oops. So when I have this kind of a setup, for some reason I seem to be liking, oops, liking light blue today. So this is the metal. So the idea is when I'm applying the VG here, of course, like it has to be with respect to some reference terminal. So almost always this substrate, the body of the device, is going to be grounded. So this is going to be grounded. Therefore, VGS refers to the gate substrate voltage. Substrate voltage. However, like for device controllability and other constraints, it is also like quite more often than not a practice to ground the source as well. So I have my source and drain here. Drain, and let me call the substrate SS. So this terminal is also grounded. So like sometimes people might refer to this as the gate source voltage, but that is the gate source voltage only when this situation is happening. If VS is connected to some other voltage level, then VGS here actually refers to the gate substrate voltage, and almost invariably the substrate is grounded. The reason for that is I want this device, not this device, I want this region to be charge neutral. I don't want any excess charges here, because as you will see in the next week's topics, any excess charge present in this substrate will actually drastically alter the behavior of the device. In fact, it might even cause the device to burn. So that is why, as standard practice, this is always grounded so as to draw away any excess charge. And the gate voltage, the channel inversion, and everything occurs as a result of the voltage difference between these two terminals. The source is also occasionally grounded. In fact, very often it is grounded. Therefore, VGS is also equal to the gate source voltage as a coincidence only. Okay, so when I write VGS here, it should be understood that in general, this is the gate substrate voltage. Okay. So first we need to draw the output characteristic and the transfer characteristic. So the output characteristic first, again for an ideal MOSFET. So, oops, output characteristic. So how is that going to look like? It's going to look like so. Yeah. So output characteristic is IDS versus VDS. So y-axis, x-axis. So I'm going to have, let me just IDS over here, VDS over here. Yeah. What I would want is, remember, like previously, yeah, let me draw that and then it should become apparent. So let me assume that my device is on. So it should act as some kind of a variable resistance system. So this straight line is going to give me one resistance value. In a minute, we shall see what this flattening is. And then I will have a second. Here, then the third line that starts, goes higher up. Yes. So there is this region after which this line flattens out. Yeah. So this is my device operating at VGS1 at VGS3 all the way down and VGS2 here. So these are the variable resistance values and the current seems to be plateauing. Now first question is, what is the relationship between any of these VGS and VT? Now the device is acting, the channel IDS, like the drain source connection, is acting as a fixed resistance value for one of these VGS values. So the first thing that I can say right off the bat is that all these three VGS values, all of these are greater than VT. They are greater than the threshold voltage. So my device is in the on state. Okay. And then what can I tell about the mutual relation? The mutual relation is, so the idea is the following. Again, going back to this, there is an inversion that occurs here. So higher the voltage, stronger the inversion. Stronger the inversion means more charge carriers present in the channel. More charge carriers implies more current. So from that I can directly say the following: VGS1 is greater than VGS2, which is greater than VGS3. Now what happens when VGS is below VT? The device is off. Since the device is off, it should not give me much of a current. And that is again what we observe. So I have this black line here that is more or less stuck to the base. Like by the base I mean the x-axis all through. In fact, I will just make this line slightly thicker. Because no matter what the gate voltage is, after a certain point, a non-zero current will flow. But it is going to be significantly smaller than. I could have done this actually. I could have increased the thickness. Yeah. Too thick. It's going to be like this. Yeah. So this region is essentially the off regime. So this is Vg less than Vt. So this is the cutoff region, and this part where the current flattens out, this is what is referred to as saturation. Now, why is saturation a thing? Let us think about it from the ideal standpoint itself. Ideally, why do I want my device to saturate? Why don't I expect that the resistance just keeps on increasing? Why do I even desire a saturation? The answer for that is because ultimately I want, like, now imagine if I didn't want saturation, let us say these lines all just extended like this all across, then would I have a transistor? The answer is no. In that case, I will have just a rheostat, a variable resistance. I can just use, some external device to modulate that resistance. The point is we need transistors fundamentally to act as, amplifiers and things like that. So I will need a kind of a characteristic that will allow my system to gain some power. And for me to have a device that can lead to a power gain, I need to have a device that is capable of saturating. So that will tell me what is the maximum power I can extract from it. If I have a device that can just give me as much power as I want, then it is not truly an amplifier. Like a single resistance is never going to be an amplifier. For that to become for that device to be capable of amplifying, I will need some kind of a point where the resistance will vary. And that, again, people who have read some advanced circuit design and device properties will know that this whole notion of transconductance essentially emerges from there. When we are looking at the two terminal, four terminal model for amplifiers, we will always have a transconductance or some related parameter that emerges, which kind of tells us when my device will amplify things, when it will not amplify things. So even ideally speaking, I want this. So this is not something that is a realistic consequence. Even in the ideal limit, I want saturation. So this region is what we refer to as saturation. Again, my arguments may not have been very clear, but I'm keeping it slightly vague because I don't want to talk too much about systems. Suffice to say, any device is an amplifier if and only if it works in a finite domain. Like if it works for all domains, it is actually not an amplifier, it kind of becomes a generator of sorts. So, that's kind of not what I want. I want an amplifier to kind of saturate at a certain point so that I know my input signal has increased over a certain threshold. Like, because one more thing I can say is, if this were to be forever amplifying, then for greater and greater and greater gains, like it also violates certain energy conservation principles. So that is also not practically possible. Like, not to talk about realism, but even in a theoretical limit, I cannot say I can have infinite power or infinite energy. Okay, so that is what I more or less want to convey there. Yeah. So now let's look at the transfer characteristic. So now what is the transfer characteristic? Transfer characteristic is nothing but IDS versus VGS. And this graph will be far more easier to intuitively figure out. First and foremost, I need to mark VT somewhere over here. This is IDS. This is VGS. So when VGS is less than VT, the device is off. No current is going to flow. So let us make ourselves sure of that. So over here, nothing is going to flow. Yeah. Big black bar, no current. And then after this point, I want a kind of linear increase to think. Yeah. So let me say this is V, oops, VDS1, and then I have VDS2 and VDS3. Now again, one can ask the question. Now see, the cutoff region is very well characterized. Like in this region, the off region, nothing, no conduction takes place. So I can define the off region over here. And it is on in this side. Now this gives me various rates of increase. And from here it's actually rather intuitive to see that the more the charge that is available, the higher the current. So increasing VGS will increase the charge that is available and therefore the current is increasing. Now even with a lesser charge, I can have more current if the driving voltage is larger. Therefore from that I can directly say the following. Oops. I can say the following. I can say VDS1 is less than VDS2, which further is less than VDS3. So again, this is just from most common sense reasoning. Okay, so this is the ideal transfer characteristics. Now, what I would suggest some of you try to do is, if you observe, there are two input parameters. There is VGS and so let me write that here. So output of a transistor is equal to IDS, which is equal to I of VGS, comma VDS. So this is a current that depends on two voltages. So technically speaking, I can make kind of a 3D plot. And this VDS is the threshold voltage. Like after this VDS, I want my device, no matter what the operating scenario be, I want it to kind of stop, like stop increasing the current. So I would actually suggest that some or anyone, try to plot this as a 3D plot and see what happens. Like if you can choose your parameters and stuff appropriately, then you can actually make a very nice 3D plot of IDS versus VGS, VDS, and then you can see these different curves as vertical or horizontal slices, not horizontal, vertical slices of two different kinds that will give me these transfer and output characteristics of the ideal MOSFET. It's just a fun exercise. I suggest that someone try it out just for educational purposes. Yeah. Now we are down to the problem on which we shall be spending most of our time. If all of you understand this part, then the assignment and any potential exam questions that may arise from this topic will be kind of covered just in this. You just need to understand what is present in this problem. So I will take my time, I will go slowly, I will explain these things as clearly as I can. And then, there is one small numerical problem in the end, and with that, we will finish today's session. So, first things first, describe all the non-ideal characteristics of a MOSFET that result from the material properties of the terminals. Now, I hope you can see what I was meaning. The notion of non-ideality comes from the fact that it is made of some realistic material. And the material properties will like infuse the device with some characteristics which I will expect to observe. Okay, so now let us see what they are. And then, the second part is to obtain an equation for the output characteristic of a real MOSFET. Okay, so just 1 second. Alrighty. Just 1 second. Where is that? Here. Yeah, okay. So let me start with a new slide for this one. So first things first, a non-idealities of a non-idealities or non-ideal behavior in MOSFETs. So first thing that we shall be looking at is non-ideal behavior of VGS. Because after all, that is the voltage that turns my device on or off. VGS. Okay, so let us quickly go back and look at the band diagram of our, or I'll just draw it here. So my N channel MOSFET, so the band diagram is going to be something like this. That was rather atrocious. Yes, slightly better. Yeah. So have my Fermi level running through. Now, the first question I want to ask is what will happen when, or rather, okay, since we are not in live interactions, the first question I would like you to ask yourselves is what will happen when I apply a voltage? So, this is my source, just so that we remember what these regions are, my gate and the drain. Okay, what is going to happen when I apply a VG here? When I apply a VG here, these are electrons present here. So the energy is negative of charge. So let me write that here as a reference. Q is minus, or rather 0.9 Coulomb, and E is equal to minus Q, or rather electronic charge equals minus Q. So increasing VGS will actually bring this down. What's going to happen is this barrier here is going to come down. So VG going up implies VGS going up implies barrier goes down. Now, what is the problem of that? Like, what is the big deal? The problem is this. This barrier is what that prevents the current from moving from the source to the drain. Now, if the barrier starts lowering, then I will actually have a situation like this. Let us look at the output characteristic. Now, VDS starts all from zero and the current is rising steadily when the device is on. Now, let us say I have a VGS for a MOSFET that is just below the threshold voltage. When it is just below the threshold voltage, what will happen is the following. Like, so let me just look at this line here. Let me see. Okay, so let me say I have this is VDS versus IDS. Now, increasing VGS. Now, let us say at a particular VGS, I have this kind of a curve. I'm not even going to bring it to the origin. Let me say it goes like this and it saturates like this. So there is a linear region and then it kind of saturates. So this is at VGS1. Alternatively, I can have a second VGS, let us say, the one is too big, VGS1. Alternatively, I can say that there is a second VGS where this voltage is slightly higher. Sorry. Or let us say this voltage is slightly lower. Let us say it has gone slightly below the threshold. Only very slightly. It has not too small compared to the threshold voltage. Let us say VGS1 is approximately equal to VT, or let me say it is VGS1 is greater than VT, so the device is definitely in the on state. Then I have VGS2, which is less than VT, but it is also comparable to VT. So, it's very close on the lesser side. The device will not turn off so rigidly. It is not like even if I go 1 microvolt below, VGS and the device will turn off. The answer is actually not that. because even close to that, this barrier lowering is going to happen, which implies the current will start flowing. Only it will not start flowing at a rate as shown here. What's going to happen is it's going to move slightly to this side. Instead of beginning at this voltage, it will begin at this voltage and go something like this. Saturate over here. So instead of rising like this, it might rise like this and go this way. This is VGS2. Okay, this is the relation between. So like it is, the order is VGS1, VT and VGS2, but VGS2 is very close to VT. So this swinging, this displacement of my output characteristic, this sliding of the output characteristic is what is referred to as the sub-threshold swing. Because ultimately the mechanism is just a band barrier that raises and lowers according to the applied voltage, and because of that the current will actually start flowing even below the threshold voltage. And my ideal behavior, where I wanted all currents to start flowing from V equal to 0, VDS equal to 0 and arrive at the same threshold voltage, all of that is not going to happen. Saturation voltage. See, here saturation is occurring at this voltage. Over here saturation is occurring at a different voltage, at a higher voltage. So the saturation voltage also loses its uniformity, its constants. So this non-ideal behavior is what we call the subthreshold swing. Okay. And how do we measure the subthreshold swing? So the subthreshold swing is referred to as SS. And so the subthreshold swing is defined by this quantity. It is d log to the base 10 of IDS. IDS divided by dVGS, essentially very, and this is applicable only very close to the threshold. This is not for voltages greater than the threshold, because for voltages greater than the threshold, this behavior is more or less followed. We are only concerned with voltages slightly less than the threshold voltage. Just let me take a break for a quick second. Yeah, and coming back. So, yes. So it is the reciprocal of this quantity to the power minus 1. Okay, so the reason why I'm doing this and not writing it as dVGS by dIDS is because IDS only comes after a VGS is applied. Like I cannot make the current flow and then derive a voltage. So technically speaking, that is what I would like to see. I'd like to see the shift in the IDS as VGS is changing and VDS is held at a constant. And ideally speaking, this quantity should be greater than or equal to 60 millivolt per decade. A decade is a tenfold increase. So log 10, I think the factor will be, yeah, I will get a +1 on this side. So essentially my gate voltage, I need to vary it by at least 60 millivolts to get this kind of a swing. So in that case, of course, my device's sensitivity to the gate voltage becomes that much lower. Like my device should only be concerned if VGS is greater than VT or if it is less than VT. That is all. It shouldn't worry too much about the fine difference. So this number should actually be very large. Okay. Like it should be on the larger side of things. And if we know about the operating voltages of such devices, you know that this value of 60 millivolts is actually pretty reasonable. So this is the non-idealities arising from VGS. The next part is non-idealities arising from VDS. Again, we are going to use the same notion. So let me start with the same band diagram. I have my gate source and source gate and drain sequence. Now, let me just look at the conduction path. Okay, so let us just translate this guy over here. So I have EC varying as follows. Now, this is my source side and this is my drain side. Now, when VDS is greater than 0, what is going to happen? Of course, this is going to get lowered. So what I will see is the following. This, rather than being leveled on both sides, is going to be going up. And then at a certain point, it will start dragging itself down. And oh no, 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 no. Sorry. What's going to happen is it's going to be like this. Pretty much the same curve all the way. But over here, it will start dragging down. So this will kind of get dragged down. Now, what does this change? What this essentially changes is this leads to an increase in the current, because remember, as my electron starts from here and reaches here, its potential energy on the band is lowered. Or rather, sorry, potential energy is not lowered. The sorry. The to come out on this side, the electron has actually reached a lower energy state, like it is not at the same energy. Which implies when the electron moves from the source to drain, somehow mysteriously it is at a lower energy level. It is, having more lower energy levels open to it. So the rate of my currents increase will actually not be very linear. It will become kind of sub-linear. I hope you can see that. See, previously, in this case, an electron with energy, let me say E in over here, will have E out over this side once it crosses the barrier. And I can say E in is approximately equal to E out. Whereas here, I have E in over here and I have E out over here. And I will expect E out, I can see that E out is less than E in. So the process of the electron being carried from the source to the drain via VDS is somehow reducing the rate at which, like the higher the VDS I have, the lower the energy states that are available. So how will this effect like manifest itself? So what is going to happen is the following. So remember my ideal characteristic. Remember the ideal characteristic of a MOSFET. Okay. So, ideal characteristic of a MOSFET looked like this. So straight up, then flattened out. Oops. And then flattens out over here. So this is VDS, this is IDS. Now what is going to happen is, if this kind of a situation occurs, then as VDS is increasing, my current line is not going to increase as much as this, because again it's arriving here with slightly lesser energy. It will still increase, but it is going to be slightly below this. Okay, so that is up to the threshold point. So now the current is not increasing as quickly as I expect it to increase. It is kind of showing some nonlinear behavior. And now there is another catch here as well. So just 1 second. Let me just draw the threshold line for reference so that I can better represent this effect. Yeah. So start from here, and it is coming out slower here. Now, assume saturation has been achieved, but the problem is this: as VDS still keeps increasing, lower and lower and lower energy levels are being exposed. So the point is, even though there is a barrier here, electrons will be more willing to move to the lower energy state, because ultimately all particles, all physical systems, they tend to de-excite and move to a low energy state if such energy states are available. So even after saturation is achieved, the current is not going to plateau. It's not going to flatten out. It is actually going to, no, what was that? It is actually going to keep on increasing. It will not flatten out, and at some point it can also feasibly cross over the desired saturation level. So first, in the active region, it kind of acts as a nonlinear resistance, no longer a linear device. So yes, I should have mentioned that here. So this region is the active region. I should have written this right here. But again, many of you know this. So this is the active region, also called the linear region. So first and foremost, linearity is destroyed, and then saturation is no longer saturation. The current still keeps increasing. So this notion of where this barrier effectively is lowered, like this energy barrier, there is a lowering of the energy barrier. So this quantity is known as DIBL, and in fact at higher and higher voltages, even this point will start lowering. Okay, so essentially I will have a situation like this where this goes up all the way and then starts dropping here itself, and kind of arrives over here. So this difference is Q times, Q times VDS. Okay, so this energy difference here is Q times VDS. Now, higher the VDS, the more this will lower, but the point is now the barrier properties also change. Therefore, this kind of a current profile is what we end up getting. So this line is ideal. And this is the real behavior. So this is called DIBL, and DIBL stands for drain induced barrier lowering. So these are the two nonlinear effects. Now, can we incorporate the effect of these two quantities to our current equation? That is the second question. Now, ideally, I want this DIBL to be less. How do I achieve that? Now, you can actually see one way of how to achieve it. Now, why is my current increasing after the threshold? Because low energy levels are available and kind of the electrons just through excitations are moving. Now, what is that excitation? That excitation is actually the slope of this energy. So this is essentially the potential energy and the electric field. So yeah, very problematic term to refer to because we've been using E for the. So let me say E vector electric field is equal to minus dV by dx. So this V is in this case EC. So I hope this notation is clear to everyone. So this is the gradient of this. Now I want this electric field to be as small as possible. Now for this quantity to be as small as possible, there is one thing that I can do. I can actually make this distance very small, because the larger this distance, then greater the voltage change will. Wait, am I telling this correctly? Yes, I am telling this correctly. So the point is, if my channel length is very short, then my barrier will not have a time to react to this electric field. The electric field lines will not connect. So for that, I will have to look at the channel and see, like, the electric field lines are going to be. So let me just write the electric field lines here. So remember, the curvature of the electric field lines gives me the magnitude of the electric field. Okay. So like if there are two very high charges, the electric field will curve very strongly next to them. Okay. In the channel. So if I have a long channel, then, and this is Vs and Vd, then Vd minus Vs is going to give me electric field lines that will kind of move like this. It'll be like this and like this. And eventually there is going to be a field line long enough to connect these two, which implies it will start accelerating electrons across the channel. Okay, in fact, these electric field lines have to be symmetric. I'm really sorry that I could not make them symmetric. Okay, now in a short channel, this curvature becomes very strong. Okay, so you know what? Let me very quickly copy this whole thing and move it to a new slide, because I still have time and this warrants a reasonable discussion, because shielding and stuff like device cleaning and things like that are stuff that you will study in the subsequent weeks. Oops. Oh, please go away. And let me, oh God, paste it as a picture. Okay, yes, I draw it again. So first, let us look at the electric field lines. In a MOSFET channel. Okay, so first, like, this is the long channel. So if I have a long channel, then my field lines will look something like this. So I will have very, like, in that case, minus dV by dx is going to be a small number. So that will effectively tell me how, these lines vary. So they are going to be like, connecting it like this and like this. And more lines, like they're all emerging from this point here. Okay. So and then and eventually I will have something that is connecting all the way here. Similarly, I will have here, here, here. This means that it's an electron starting here, even if it does not have sufficient energy, can gain enough kinetic energy as it is crossing the channel to reach the other side. So that is essentially what happens when this barrier is lowered by the drain voltage. However, if I have a short channel, oops, if I have a short channel, then what happens is, let us say I only have this much. Then the electric field effects are going to get truncated over here. This field line will not appear. So only the field lines that end up to this point will appear here. Okay, so they are going to be this, 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 hold on. This, only. And let me use the blue one here. So they're going to be, and yeah. So in this case, what's happening is, even if an electron were to get accelerated through the channel, what's happening is it won't ultimately reach the drain. So yes, there will be an electronic excitation due to the drain induced barrier lowering, but it will not contribute to my current. So this increasing trend will vanish. And this is essentially what is known as electromagnetic screening. My God, I was about to say screaming. Screening. So this automatically implies DIBL is lower in short channels. And this is one of the most direct benefits of studying nanoscale devices, because nanoscale devices all have short channels, therefore by definition are resistant to DIBL. Not resistant, they are protected from DIBL. So I can actually have better saturation characteristics, and that implies when I can swing my voltage between the saturation voltage and the cutoff voltage, I can have better switching characteristics also, which is ultimately what we desire, because we don't want to build power amplifiers using nanoscale MOSFETs. No, we want to build better switches that can work in digital electronics devices. So that is where we want these devices to work. We want them to be very good switches. So short channels are inherently favoring such behavior. Now let us derive the equation. So that is going to be the last 5 10. I hope I've done a reasonable job of explaining the various non-ideal phenomena. Okay, so now let us try to derive the current flowing through a realistic MOSFET channel. So part B, current flowing through a realistic MOSFET channel. So over here, I'm going to do something that I said I will not do, but I will do it nonetheless. And you will understand why we are doing that. So there is a there is effectively two junctions present in my channel, right? So this is EC, and this is my source, gate, and drain. So I have ILR, I left to right, and I will also have an IRL IRL from right to left, essentially flowing across this barrier, flowing across this barrier. Okay, so I will just treat it like that for a second. Okay, and this is EC at the source, EC at the drain, at the channel. So this gate is essentially what I shall also call the channel. So this is the channel. Uh, yeah, channel. Okay, so now the electron flow essentially comes from the Schottky equation. So ILR, which is flowing from here to here, is some saturation current IS e to the power minus E source channel divided by KBT. E is the energy, remember, and IRL is IS e to the power minus E ds or DC, sorry, divided by KBT. Okay, now the net current IDS is ILR minus IRL. So this is going to be, just look at these two and write it as this. So this is equal to IRL into 1 minus ILR by IRL, and just substitute these expressions. The IS will cancel out, and what we will have is 1 minus e to the power. Essentially, I will have ES minus EC minus EC minus ED, ES minus ED, that will be equal to minus Q times VDS. So ES is ESC is ES minus EC, and EDC is ED minus EC. And so this is, I will make the things correct here. So I will say this is ES, EC, and ED. Now, of course, since there is a VDS, yeah, I should also make that correct. This is going to be slightly lowered. Oh God, that whole thing's going to vanish, is it not? Yep, thought so. Okay. Yeah. Yes. So this energy level right here Yeah, sorry for this last minute chaos. Yes, much better. Yeah, so this is what I'm calling ED. And this energy level right here is what I'm referring to as EC. And right now, I'm, kind of, whatever the highest value here, I'm taking it as EC. There may be some DIBL, there may be some, threshold lowering because of VG. Whatever it is, the highest point So EC is, let me also write that. EC is highest energy value in channel. Okay. Another thing that I can say is if that is the case, then I know that DEC by DX is equal to 0 because that's a maxima point. Okay. This implies the electric field E vector is also 0. So I'm actually going to that point in my channel where the electric field is 0. Okay, so that is what EC signifies. Now, if you substitute all the values here, you are going to get this. I am not going to bother deriving that. By now, you should all know that. If you have any doubts, please raise them in the forums. I shall address those questions then. Okay, times, let me write it like this, IRL. Okay, so now this gives me the first relation. IDS upon IRL is equal to this quantity here. 1 minus e to the power minus QVDS divided by KBT. Okay, now the next quantity that I will be like trying to evaluate is Q, and let me say that point, let me say, so this corresponds to x equal to 0. So this point where I have the highest, so this is the point that I'm going to call x equal to 0. Like in a realistic scenario, I may even have some DIBL and other threshold effects affecting my channel so as to do this, but I am considering this energy here for present purposes. I can just model this as a very large junction with a very wide depletion layer. Even then these equations, these Schottky equations will hold. Okay, so now Q at x equal to 0, that is what we are trying to derive. Q at x equal to 0 can be seen as, now when the electric field is 0 at this point, that implies there is no force on the charge, so all the charges present there will be static. So where are the charges coming from? They are coming from LR and RL. So they are both getting accumulated at this point. So that is a point of charge accumulation. So that is going to be equal to IRL plus ILR divided by W ut. Now you can ask what this W is. W is essentially the width of the channel. So W is this quantity, the width of the channel. Okay. So W, and remember, oh yeah, I can quickly go and show that. I should have mentioned this before itself. This is a 3D object. In this 3D object, this small slice is where the conduction occurs. So I can directly say this is a quasi 2D channel device. So therefore, it is actually very fortuitous that in the previous slide we have done all the necessary derivations for quasi 2D channel dispersion relation and density of states in this presentation itself. So it makes reading easier. Okay. So this width is the width of that 2D channel. Essentially, it is the width. In this figure, it is how deep into the slide this goes. So the width is measured in this direction that goes into the slide. Okay. So although like of the quasi 2D channel. Okay. So and Vt is the thermal velocity. Like that is the rate at which the electrons will either ways move out. Okay, so now this is the thermal velocity here. Now from this I can write the following: IRL into 1 plus ILR upon IRL into 1 over W times the thermal velocity is the charge. Now I know what IDS by IRL is. Okay. So additionally, I can say one more thing. IDS is W into Q at x equal to 0 into thermal velocity. So this is essentially, the definition of the current. Whatever charge is accumulated here in this point, it is pushed by VDS. Okay, not VDS, it is pushed by the thermal velocity. So that is the current that I will expect. So from this, I can equate this to IRL times 1 minus ILR by IRL, and then I can substitute the value of Q over here. Okay, so now that is going to give me the following. So the W times newt is going to cancel out, and from this I will get the following value for the current. So Vt into, now this quantity will, okay, yeah. So I know IDS by IRL, so I can, yes, so this is a, now equate this and substitute this over here and try to get out the expression for IDS, and you will get this quantity finally. IDS is equal to 1 minus e to the power minus QVDS divided by KBT divided by 1 plus e to the power minus QVDS by KBT. Now setting e to the power minus QVDS upon KBT. Yeah. Oh, yeah. What you can do is essentially write IRL in terms of Q and this ratio and just substitute it over here. So that is what we will get. So this implies IRL is equal to Q at x equal to 0 into, oops, W into Vt into 1 divided by 1 plus ILR divided by IRL. Yeah. So just substitute this value over here. Okay. Yeah. This is not correct. Therefore, IDS is equal to this. So that is going to give me this. And this quantity is what I shall call I naught. So this is technically the transistor's saturation current. Okay. And so what you can see here is it is 1 minus, yeah, so let me set this to be some x. So this is going to be I naught into, or rather, let me write it like this because I should not just, let me say this. Yeah. x. Then I can write this as 1 minus e to the power minus x divided by 1 plus e to the power minus x. You can multiply this by e to the power x by 2 in the numerator and denominator and see that this will actually be the hyperbolic cotangent function because e to the power x minus, no, hyperbolic tangent function. So this is going to be tan hyperbolic of x. Now how does the tan hyperbolic function look like? You can actually, let me make a new slide and plot that. So for very low values, so let me, IDS is equal to I naught into 1 minus e to the power minus x divided by 1 plus e to the power minus x, which is equal to I naught into tan hyperbolic of x by 2. So this is the actual functional value. Just look at this here. For very small x, this quantity, okay, so for small x, e to the power minus x is approximately equal to 1 minus x. Standard approximation. So IDS equals 1 minus x divided by 1 plus 1 minus x into I naught, which is equal to I naught. I will not get rid of the x above because that is the only quantity there. If I remove that, the numerator becomes 0, which it won't be. So this is going to be x naught, but 2 is very much greater than x. So 2 minus x is still approximately 2. So for small x's, this is going to increase somewhat linearly. So let me have a plot of that ready. Okay, so this is the realistic IDS versus VDS. Remember that VDS is actually proportional to X. So, the same principle, like if X is small, then VDS is also small. Okay, so for very small currents, this is going to be more or less linear. So my curve is going to be something like this. Kind of a straight line for very small x. Now, what happens for very large x? For very large x, this quantity kind of like tends to 0, but remember that the like e to the power minus x will tend to 0. But remember that always the denominator is going to be smaller than the numerator because this is a small number close to 0 being added and this is a small number close to 0 being uh, subtracted. So it will have a fractional value that is always greater than 1. So as VDS is constantly increasing, this line will kind of never straighten out. And in between, the tan hyperbolic function actually looks like a tangent function. So the graph will rise like this, slightly, oh no, it will actually rise like this. There will be an inflection point somewhere in the middle, and then it will kind of peter out. Now for a lower VGS, which implies lower charges and lower everything, similar graph will rise up and go this way. And for a slightly higher VGS, this whole thing will rise faster, more or less this way. So this is VGS1, VGS2, and VGS3. again, just in shorthand, 1 greater than, oops, 1 greater than 2 greater than 3. So this is how the realistic output characteristic of our transistor look like, more or less. And these things you can use any, like you can actually introduce the device properties and use any device modeling software to observe these characteristics. You can numerically derive these things. You can even do quantum mechanical techniques to kind of verify the same things. So yeah, we're done. Now down to the last question. So at a given rate, a given voltage, gate voltage, the drain source current IDS is measured at VDS is equal to 26 millivolts. Now find the factor by which the current will change if the value of VDS is doubled. Now why did I say 26 millivolts? So assume that the device is operating at 300 Kelvin. So the catch about 26 millivolts is the following: KBT, KB into 300 Kelvin is equal to 0.026 or 267, yes, volts, which is equal to, is it 267 or 257? I think it's 257. Yeah, not 267, it's 257 or something like that. Okay, which is approximately equal to, not equivalent to. So this is essentially the thermal voltage, 26 MV, which is V thermal at 300 Kelvin. So if this is the case, then X is equal to QVDS divided by KBT. Oh, shouldn't, it should be milli electron volts. I'm sorry. Milli electron volts, and this should be electron. This is units are energy. So if I multiply and divide by all these things, then I will get X is equal to 1 in this case. Now if X is equal to 1, then what is my IDS according to the previous expression? This is I naught into 1 minus e to the power minus 1 divided by 1 plus e to the power minus 1. So this is what my I naught is. So what is this going to be? We can directly evaluate this because I've chosen an appropriate voltage value. So this is going to be, let me quickly calculate this. Uh, yeah, so this quantity is going to be something like 0.46 I naught. Not too much actually. It's going to be a very small current because again the voltage is very small. Now the question is, what will, by what factor will the current change if VDS is doubled? If VDS is doubled, then I will know X prime is 2 times QVDS divided by KBT, which is equal to 2. Both of these are at 300 Kelvin. Temperature is kept the constant. So now IDS in that case is I naught into 1 minus e to the power minus 2 divided by 1 plus e to the power minus 2. and this will come out to be 0.76. And anybody who bothered to guess that, see, x is very small, smallish, and I can do the approximation, you'll see that the values are actually not too far off. If you just doubled this, you'll get 0.92. 0.76 is almost there. The error is, just it's under like 20%. So even the linear approximation holds to values of x where x are like whole numbers. It's 1 and 2 and things like that. So now the factor by which the current will changes. So this is IDS prime. So IDS prime divided by IDS, that is going to be 0.76 divided by 0.46, which will be come out to 1.65. So this is the factor by which the current increases. So this is how numericals are done in this. Yeah, I technically don't. For the members who are attending live, I apologize for having taken the extra time. And for the people watching, well, if the video, I mean, if you have reached at this point, there is nothing I can do. You watch the whole video. But the slightly longer session I took so that I can explain these non-ideality effects and derive these equations properly, so that it becomes easier for you to answer these questions. So yeah, with that we come to the end of today's discussion. Next week, we will start with MOSFET electrostatics, where we will see the actual impact of this gate voltage. Like, what does it change? What is the inversion charge? How do I measure the amount of inversion charge that is present? Does it vary linearly, non-linearly? What are the non-ideal effects that I may see there? So those are the things that we shall be looking at in the case of in next week's syllabus. So once again, I thank you all for attending the session live and watching the session online. So with this, I bring this session to an end. I will see you all again next week, same time, and also belated Holi wishes to all attendees. Okay, yeah. So I shall stop the recording now and end the session.